Hello friends. In this video, actually this is a continuation of a series of videos about understanding cyclicness of an integer and general cyclic group. Today we will see the connection between integers and general cyclic group. You may have noticed that the cyclic group definition something to do with the Z, right? The indexing set Z. It plays much more than that, okay? It plays a much more vital role than that. Now, basically, this looks like a power 0, that is what identity we say, a power 1, a square, dot dot dot, a power minus 1, a power minus 2, dot dot dot. This goes in both the direction. Of course, in the finite sense, maybe like in the finite case, it will cyclically repeat it. You may get only finitely many elements, okay? So let us understand them. So I start from here, Z and the general cyclic group. Take a general cyclic group. Finite, infinite doesn't matter. Now I'm going to send a map. How I'm sending a map? N going to this. The moment I say cyclic, it is generated by some element. Pick that element. Fix that element and a power n. You may fix according to you, doesn't matter. I fix one of the element. Okay, any generator will do. So climb. So let's say this map, right? P is homomorphism and on to homomorphism, right? So how am I going to do that? To show that this is homomorphism, I should start from n. N maps to a n, m maps to a m. So what is phi? N plus m plus n is nothing but a m plus n, which is a m into a n. Exactly. That's what we saw in the last class, right? Okay. So that is actually phi of a m dot phi of a n. I should put it like this. Sorry, n, which is the homomorphism, right? Homomorphism. And to prove onto is very simple. Just that understanding. Only one thing is understanding. For any x belongs to the codomain, there exists a m belongs to natural number. Not natural number, integer, such that x looks like a power some m. Choose that m. So phi m is equal to a power m, which is x. So it is on to homomorphism. Now the role of fundamental theorem of homomorphism or first isomorphism theorem. We like to call first isomorphism theorem. Isomorphism theorem. That is, whenever you have a group and there is a onto homomorphism from another group, then let's say onto homomorphism, then G by kernel of phi isomorphic to star. I'm assuming you have some familiarity with the definition of kernel, homomorphism, and all those things. And first isomorphism theorem is so fundamental. It's like a coming and helping our thing, catalyst. And this is one of the things we wanted to understand. So we will later on see proofs of this in some other video, but let us understand here. So we have a homomorphism from integer, right, to the general cyclic group. General cyclic, which is generated by here, and which is onto. And namely, that is going n going to a power n, right? Now, that says that C by kernel of phi isomorphic to G. So we got a very nice thing. And the kernel of phi is subgroup of Z. And we know all the subgroup of Z looks like nz for some n belongs to natural number union 0. So that says that Z by nz, I'm including the possibility of 0z isomorphic to G. That is, G is isomorphic to either Z. Okay, either Z, depending on the kernel. Kernel trivial. If otherwise, kernel is non-trivial, this is Z10. So we got a very nice classification, very beautiful classification. This conclusion number 1 is G is isomorphic to Z if and only if G is infinite. So this is a conclusion. And 2, G is isomorphic to Zn if and only if G is cyclic. First of all, G is cyclic. Cyclic, and you know that size of G is n. Because of the one-to-one onto-ness, there is a one-to-one onto-ness, so the group things should be equal. So finally it boils down cyclicness and the size. So final conclusion, after all this work, we can say that G is isomorphic to Zn if G is cyclic plus order of G is n, or G is isomorphic to Zn if G is cyclic and G order of G is infinite. That's it. So we have 2 choices only. So that's why I keep on saying that Z and Zn are the very good and the most important examples. Now using this classification, one may ask lot of questions. Now this ends the classification. So what is the classification? Anyone can conclude now. If G is cyclic and order n, that must be isomorphic to Zn. If G is infinite and cyclic, and that must be looks like nz. So all subgroups except 0, right, nz's are isomorphic to Z, where n belongs to natural number. So this Zn, so you can say that this is isomorphic to nth roots of unity. The general nth root of unity is it's a complex number Z. This looks like e power in. The Z is looks like, you can see that thing, e power in k by n. Am I right? Okay. K running over 0 to n minus 1. 2 pi I k by n. Okay, when I put this power n, it will automatically go. So these are the elements. So this is isomorphic to Zn. So now one can ask a lot of questions. How many generators Zn has? What is the connection between one can go from here to here? So each generator, using this, you can get a generator here. Those generators are called the primitive root of unity. Many questions can be answered later on. Okay. This ends the classification, at least theoretically. We now have to see some of the deep application, starting from slowly one by one, and see the beautiful applications. Okay, group theoretical application of some facts of number theory, some other facts, and so on. I will add those videos later. Thank you, and subscribe the channel, share to the friends and math related people. Okay, thank you.